In this video, we're going to talk about impulse responses. The impulse response is the property of a linear time invariant system, and we're going to need to understand impulse responses before we can start talking about convolution. Let's assume we have a linear system with some unknown features. We don't know if it's a high pass or a low pass. It's just a system. And as we've learned all along, we can take any input signal we want. We could take a cosine or a step or whatever we like and place it into this system. But today, just for the sake of argument, I'm going to take a very special signal and apply it as input. And the signal that I'm going to apply as input is going to be an impulse, otherwise known as the delta function. So an impulse is something that's infinitely skinny, but also infinitely tall. And in this case, unless otherwise marked, you can assume that it has an area of 1. So think of it as a rectangle whose area is 1, that's infinitely skinny and infinitely tall. And I'm going to take that impulse and I'm going to apply it to my linear system. Okay? And again, every system will respond differently to an impulse. So what I'm going to draw you is just an example of what an impulse response might look like, and it'll be different for every single system. But for now, let's assume we're working with a system and we apply an impulse and we measure the impulse response, and that impulse response of course starts at time t equals 0 because that's when the impulse arrived, and let's say it looked like that. Okay? So essentially what we're doing is we're taking our system and we're whacking it with a hammer. And we're looking to see how it responds. Does it shake? Does it vibrate? Does it move a lot? So basically, the way that the system responds in response to an impulse, it tells us some sort of it'll respond somehow according to the properties of the system. So just to write out what we've done, we are taking an impulse. So the input is the impulse, which we refer to as delta of t, and by definition what comes out is the impulse response, and traditionally that's referred to as h of t. Okay, and again, it should make some sort of intuitive sense that h of t should somehow capture the properties of the system, the features of the system. Okay? And that's what we're going to learn. We're going to learn that h of t tells us a lot about how the system operates. So let's take a minute to think about what this means. If we were to take the Fourier transform of the impulse, okay, so let's think about this from a frequency perspective. So let's say we want to take the Fourier transform of the impulse. Okay, so what frequencies am I putting into this system when I apply an impulse? Well, we learned earlier in the semester that the Fourier transform of an impulse is actually the constant 1. So really, when I apply an impulse to a system, really what I'm doing is I am applying all frequencies at the same time. Right, all frequencies simultaneously. Right? It's almost as if I'd taken all the possible cosines in the world and applied them one by one to this system, and now I'm going to look to see how my system responds to each of those cosines. So if my input is all frequencies, then by definition, h of t has to be the system's response to all frequencies. Let me just jot that down. It has to tell us how the system responds to all frequencies, because that's what we put in. We put in all frequencies. What we get out is the system's response to all frequencies. So it might stand to reason, what do you think would happen if we took the Fourier transform of the impulse response? Well, it turns out that if the impulse response is the system's response to all frequencies, then what you should get is the Fourier transform h of j omega, the transfer function. This relationship will always be the case because they're essentially telling you the same thing. H of t is the system's response to all frequencies, and h of j omega is also the system's response to all frequencies. It's just that one way you're getting that information in the time domain, and in another way you're getting that information in the frequency domain. Let me give you an example. For a first order low pass filter, we can prove using differential equations that the impulse response can be given by the equation 1 over RC e to the minus t over RC for t greater than 0. Okay, that is the impulse response. And if I were to then take the Fourier transform of that impulse response, let's see what we get. So I'm going to apply the Fourier transform integral. I'm going to integrate from t equals 0 to infinity, 1 over RC e to the minus t over RC times e to the minus j omega t dt. So that's just applying the Fourier transform integral. And if I work the calculus for a moment, the 1 over c comes out. The exponents can be combined. So I'm going to choose to rewrite this exponent as e to the minus 1 over RC plus j omega t dt. And so in essence now what I'm doing is I'm integrating e to the at, which should be 1 over a e to the at. And in this case, my a is going to equal to, if I combine that into a common denominator, it should be minus, let's see if I can get this right on the first try, 1 plus j omega RC over RC. Okay, that looks right. So putting it all together, I have 1 over RC times, actually I'm not ready for that yet, times 1 over a. So the 1 over a will be RC over minus 1 plus j omega RC times e to the at. So e to the minus, and I'm just going to put parentheses just because I don't feel like rewriting all that stuff, from 0 to infinity. And then I'm going to notice a couple things. First of all, I'm going to notice that the RC's cancel. Then I'm going to notice that when I substitute in infinity for t, I get 0, because e to the minus infinity is 0. And when I substitute in 0 for t, I get 1, because e to the 0 is 1. So we have 1 over minus 1 plus j omega RC times 0 minus 1 equals 1 over j omega RC plus 1, which is the transfer function for the low-pass filter that we all know and love. So this relationship will always be true. The Fourier transform of the impulse response will always equal the transfer function. And that's a property that we're going to exploit in order to do time-based analysis of system dynamics.